Hello and welcome to my video, a 2D vector question about rivers. Now it's not just rivers, but that's kind of the normal. Okay, so we're going to look at the normal. We'll take a look at a plane, but this could be used in many different examples where there is multiple forces happening. But these two are really good examples. Another one I can think of right now is a treadmill. If you have a treadmill and a ball going on it at an angle, it kind of would do something weird. So I've thought about what that would look like, or maybe not a ball, but like a remote control car. So anyways, there are more examples than this, but these are kind of the two main ones. So let's go ahead and take a look. A river flows east to west at 2.5 meters per second and is 65 meters wide. A boat capable of moving at 4 meters per second crosses in two different ways. Find the time to cross if the boat points its bow directly across the river, and then find the time to cross if the boat moves directly across the river. So points versus moves. Okay, so this is going to change it quite a bit. So we've got a river, okay, flowing east to west. Let's take a look here. So river's flowing east to west. So that means the riverbank is looking like this, okay? And so this is kind of the push that if the boat wasn't doing anything, this is what would happen. The boat would drift to the left or to the west by 2.5 meters per second. But in fact, the boat is doing something. It is pointing directly across the river. Directly across the river, just like this. Now, at this point, you're thinking to yourself, what's going to happen to the boat? Well, the boat will go at an angle across the river. So if it starts over here, it's going to end up over here at an angle like that, right? But, we could calculate it, but honestly, it doesn't matter how that angle, because if it's pointing directly across the river, the distance that is going is also directly across the river. So therefore, we just need to use a regular old V equals d over t, and we're looking for time. So we're going to rearrange t times v equals d. Rearrange again, we get t equals d over v. And we can just type in our calculator 65 meters over 4.0 meters per second, and we're going to get the time it takes to get across the river. That didn't really help, but that's okay. 16.25 seconds. Now with sig digs, we should just say 16 seconds. All right. So now for the second part of the question, it looks very similar, but this time we know that still the river is pulling the boat to the left or to the west, but now the boat is going to make it so that the boat actually moves directly across the river. So that means that the boat has to point in this direction in order to make that happen. 4.0 meters per second. This is a 90, and we're looking for this alternative side. So I'm going to call this side A. The reason why I'm calling it side A is because a squared plus b squared equals c squared. This is Pythagoras' theorem for a right angle triangle, only for a right angle triangle. So this would be like this. Then it would be, like this. And finally, we'll write in the numbers. So c squared is the 4 squared. B squared is 2.5 squared, and we get an answer of, that should be a minus, Oh dear. There you go. 3.12. 3.12. This is still meters per second. Okay, and now we're going to use the same formula as before. So now we can use T equals D over V. I don't want to rearrange again. I mean, we've already done it. So D is still the same as before, and our new speed is this. So what is our new time? Well, let's go, oh, hold on. Let's go 65 divided by that, which we get 20.816. Rounds to 7, but we're going to round it to 21 seconds. And if you were curious about the angle, we could also calculate that if we wanted to, but it's not asking us to, so we won't. Okay, but you could use cos, because you've got the hypotenuse and the adjacent, so you could use cos. Okay, so here we are going to go ahead and work this out differently. I highly recommend you pause the video right now if you feel like you understand it and try this question. Okay, so here we have a runway that is going north and south. Let's just mark that out like this. This is our runway, and we've got winds that are blowing from the west, which means they're blowing this direction. Okay, let's just do that here. Okay, and we want the plane to land straight, obviously, otherwise it can't land on a runway. So we want the plane to land straight. So what we're going to do is we're going to draw the arrow like this in order to make sure the plane is actually moving straight. Okay, so the winds are blowing at 75 kilometers per hour. The plane is flying at 350 kilometers per hour. Okay, and we need to know what angle that the plane will land at so it lands safely. So we're looking for this angle theta. And basically it's just like the last question. So cos theta equals adjacent over hypotenuse. Theta equals cos -1 of adjacent over hypotenuse. And now we can calculate our answer. So this would be second function cos 75 over 350, 77.6 is our angle. And we'll use that angle there. Okay, so what angle does the plane need to land at if they're traveling at 350 kilometers an hour? That would be our angle. What is the ground speed of the plane? I should say if they're traveling at an air speed of, there you go. What is the ground speed of the plane at this angle? So this would be like a part B of the same question. Okay, so now that we've done that, you could also calculate the ground speed of the plane. So this would be, again, the same as the last question. So a squared plus b squared equals c squared. Then you just rearrange. So subtracting b squared on both sides. Then you rearrange again. So square rooting both sides. So 350 squared minus 75 squared. So A equals 342 kilometers per hour. Okay, Oh, I should say that the angle, we should actually have a little bit more to the angle. We should say this is north of west. Yeah. Or we could also call it, just so that we're clear, we could also say 90 minus. And we could get the other version of the answer. So 12.37. So 12.4, which would be, how can I label this best? It would be kind of this other angle here, which would be west of north. So either one of those two does work, but you can see that they would have some sort of angle in order to make up for a crosswind. And the crazier the crosswind, the crazier the angle. So this is, you can see this picture here of this airplane super angled, and it has to land this direction. So the plane is trying to land here, but it's angled out here. It's crazy, crazy. Okay, yeah, I hope this video helps you better understand river questions, and good luck.